All right, so this is continuing on with 11.1. We were reviewing here that the median is the middle, so half the values are above and half below. But if the mean is dragged to the left by some values in this direction, then it's called negatively skewed, okay? The tail is going towards the negative direction. Symmetric is when the mean and median are roughly the same. When the mean is dragged to the right by some values up here and most of the values are actually down here, then it's positively skewed, okay? The thing we need to know is they want us to make a decision today. If it's symmetric, all we need to report is the mean and standard deviation. But if it's skewed a little bit one way or the other, then giving the whole 5-number summary is a better picture of the data, okay? Because it's about interpreting the data. We did this question yesterday, yes? So we left off with this one. Yeah. Do you want to not take time to type all those in? Want to just go with watching me? Okay, so I have them in, I think. I pray they're still there. What is this question about, guys? Anybody? Yep. What am I entering? Or hopefully already have entered. Yes. I'm not going to cry. Maybe they're in list 1. Go back. Yes, they're there. Okay, list 1. So we advertised a 20-ounce steak, and they took the weight of, how many of them? Is that 20 of them? Looks like 20 of them. To decide if we really are averaging 20-ounce steaks because some are a little bit smaller, maybe a couple are bigger. Trying to figure out, are we really false advertising or not? Yes? Okay. So it says construct a histogram. So I put all the data in. Does anybody remember where we go to look at a histogram? It's a plot we need to turn on. Okay. And the plot that we're going to choose is the one that looks like a bar graph. Everybody okay? And then if I want the calculator to do it, I can just turn it on and do a zoom stat, which is 9. Oh dear, I have one still on. I thought I turned them both off. Okay, so this looks a little bit skewed what? Yes, skewed left or skewed negatively, because most of the data is up here. Now, they chose some size of the sample here, what we're going to count by. Probably not what I would have done. I would have said, well, starting at 5, going up to, why does it only go up to 13? Didn't we have steaks up to 20? I'm so confused. We didn't have any as low as 5. Do I have the wrong list? I bet I have the wrong list on. It says list 5. Try again. List 1, zoom 9. Definitely not as skewed as it was looking before. We're going to put in, was 17 the lowest steak, guys? Yeah. And 22 is the highest. And I just say count by ones, right? How many fell in each category? So if I graph that, okay, AP stats people, would you say skewed or not skewed? Not skewed? Okay, the other way we can do is we can go do the one variable stats. Stat, right, 1, enter, whoa, list 1, just kidding. And we want to know, are the mean and the median far apart? The mean is 19.3 and the median is 19.5. So definitely not far apart, right? So we could just go with the data is not really skewed. So the mean is 19.3 with a standard deviation of 1, roughly here. 1.05, yes. No, there can be. It, like I said, the second thing to check is if the mean and median have been dragged apart from each other. The mean is dragged apart from the median, okay? We looked and the mean was close to the median. So we decided to say it wasn't skewed. So to summarize, we would say the mean, this is really the summary that goes down here, but the mean is about 19.3 with a standard deviation of about 1. So average stake weight is 19.3. I would say he needs to start buying a few more stakes if he's going to advertise 20. A few more bigger ones. I mean, you know, making sure they're closer to 20. So, all right, moving on. This is just for you to look at and talk about a little bit. It says distributions of data are not always symmetric or skewed. Sometimes they fall into clusters. Therefore, there can be 2 peaks, and it's known as bimodal data. This doesn't happen very often, but it can happen. For example, this is the cost of college tuition. They just took 20 random colleges that came to a college fair. They said, what's your annual tuition? Well, they got this when they put them all in there. Anybody think about why they might get 2 totally separate graphs? What? Out of state and in state, or private and public, or junior college, generally cheaper, right? Community college and university. So there's lots of different reasons, okay? It says it's likely that the 11 with less expensive tuition are public and the 9 with more expensive tuition are private colleges, okay? So there is a reason that it could look like this. And in that case, if I had made you describe it, which I won't, you could describe it separately. You could say the mean of cluster 1 is this with a standard deviation of this, while the mean of cluster 2 is this with a standard deviation of this, because that's a huge difference, right? So they did them separately. All right, we talked about box and whisker plot. Again, when this whisker is longer in the negative direction, that's when it's negatively skewed. And when the whisker is longer this way, that's when it's positively skewed. All right, 5-number summary. Does everybody remember where to find that? That was when you did the 1 variable stats and then you scroll down to the bottom, these 5 numbers, min, Q1, median, Q3. So tell me again what I might say in words. All of the stakes weighed between 17 and 21 ounces, right? With 50% being between 18.5 and 20. The Q1 and Q3, the middle 50%. But because 20 was Q3, I'm not sure he should be advertising really only 25% weigh 20 ounces or more. He should need to fix his advertising. All right. Interquartile range is, again, the difference between the quartiles, Q3 minus Q1. And outliers, we decided we were just going to let the calculator do that for us. All right. Do we need to do one of them together, guys? Can you enter these real fast? This isn't too long. Want me to read them? Stat, enter, 5, 7, 9, 11, 13, 10, 9, 8, 7, and 5. Okay. A shoe store employee designs a display by placing shoe boxes in 10 stacks. The number of boxes in each stack are 5, 7, 9, 11, 13, 10, 9, 8, 7, and 5. Construct a box plot and use it to describe the shape of the distribution. Okay, why do we care about shoe boxes displayed? Anyway, I have these numbers in list 2. So it said a box plot, right? So go stat y equals, turn on plot 1, make sure it says the right list, which was list 2 for me, probably list 1 for you. Do you remember which one is the box and whisker plot we want to use? Box and whisker. We want outliers, so we're going to use this guy that has the 2 little dots out here for outliers. We're going to pick that one. Now, if you don't have if you go to y equals and you don't have any other plots on or equations on, then you should be able to just do a zoom stat. Everybody's looking like this. Okay. Does not look to be too stretched out to me. Does it seem okay to you? Not that there are definitely no outliers, and it doesn't really look skewed to me. So if we went back and did stat, right arrow, calculate, make sure it's in the right list. Was it list 2 for me? Okay, so what is the mean number of boxes and the median? So they're very close together, so we don't have to say that it's skewed. When it's not skewed, what do we use? When it's not skewed, it's easier to describe the data. You just stick with mean and standard deviation, okay? So the mean of 8.4 and the standard deviation of about 2.4. All right, I would put some great interpretation into that, but it's boxes of shoes in a display. It's kind of weird data, yes. The standard deviation, which is this one, it's the little sigma x. Okay, that's the one we're using. Good question. All right, interquartile range we talked about yesterday. It is just the length of the box. And then it talks about how to find an outlier, but we did that yesterday. So I am moving on to talk quickly about this at the top of 11A. And I'm not going to make you type all these in. It's just an example. It says the ages of Oscar-winning actresses from 2 20-year periods as shown below. So from 69 to 88, these were the ages of the women given the Best Actress Award, okay? And this is the top plot right here. You will notice with the exception of 2 outliers, they're closely bunched together down here, okay? And it looks to me like this 74 is an outlier, and maybe both of these 61s. Does anybody see anything else high? So there were actually 3 people that were grouped in the outlying. From 89 to 2008, okay, there was an 80-year-old woman and a 61-year-old, and those are outliers. But what do you notice about the data a little bit here? Older, younger, more younger, more older? Can you tell from this? This 25% in the left half of this box is clearly younger than this one, right? Okay. It says from the graph, we can see that the median age, which is the middle of the box, for the first 20 years is slightly higher than the median age for the second. That's the middle of the box, was slightly higher. The range of ages for the middle 50%, the length of the box, is also slightly higher, right? For the top one. Both sets have outliers greater than the rest of the data. Ignoring the outliers, the distribution for the 20-year period is more symmetric for the first one. This is more equally spread out than the second one, which I probably wouldn't have mentioned that if I was doing it. But all right. This is data about average wind speed in the United States listed below. Different places, okay? Can we just watch this again? I just feel like it takes so long to type everything in, and I have it all in, okay? It says construct a histogram. So say I had put all the data in, or you had put all the data in. Let's see what list I put it in. I think it's 4. Yes, yes. Okay, it's all in list 4 on my calculator. Help me remember that, okay? So I put all the data in, and then it says construct a histogram. Does anybody remember what we do to turn on the histogram? Second y equals, which one is it? Yes, it's this line bar graph thing here, okay? And where is my data, guys? List 4? Okay. Now, if I do let's talk about this data for a second. This is average wind speed at different weather stations in different cities, okay? So if I were to put in just a zoom 9, it looks like this. So there's a couple that have high winds, not really dragged out one way or the other, but I usually don't like what they picked. Look they're cutting off each category by 1.26. That's really weird to me. So if I said they range from 6 to 14 miles an hour, I think it was miles an hour, and I want to say I'm going to go by 1s or 1.5s. It's fairly symmetric, yes? Okay. So summarize the center and spread using the mean and standard deviation, which I could do again. So to do that, how do we find those values? I just want to make sure you remember how to do this since I'm not actually having you type. How do you go find the mean and standard deviation, guys? No. Just stat, and then what? Calculate one variable stats, yes. This is for list 4. Okay, so the choice is the mean close to the median? Median 9.2, mean 9.2, very close, right? So we can just say most of them averaged around 9.2 with a standard deviation of 1.5. All right. Average wind speed, was it 9.2, guys? And standard deviation, I already forgot. Was it 1 point something? I don't think it's one of the things I have on the screen. Maybe it is. Nope. 1.5. All right. Then they start talking about, well, what if you want to compare data? So the second part of the question, number 4 here, everybody see where we're at? They're still using the numbers from up above. And it says the 10 weather stations with an asterisk have relatively close proximity to an ocean. Okay? Construct side-by-side box plots of the data sets, then use this display to compare the distributions. All right, do you want to try this or you just want to watch? Why don't you try this? I am going to switch a couple of them. Okay? I want you to do the yellow ones. Can you see well enough or not? I can read them. I want you to do the yellow ones in one list and then the green ones in another list. Because, so which did you start with? Okay, so like list 1, we're going to put 9.1, 6.2, 9.5, 7.1, 12.5, 11.3, 8.1, 9.2, 9.4, and 9. Okay, then arrow over to list 2, make sure it doesn't have anything in it, and we're going to put the green ones, which are not near the water. 8.9, 10.8, 10.7, 10.5, 9.3, 8.8, 6.2, 9.1, 10.4, 9.6, and 7.8. All right, they want us to construct side-by-side box and whisker plots, which means you're going to go, I got to go real quick and look where mine are. Somebody help me here. They are in 5 and 6 but I did the green ones first. What did we do first? The yellow ones? Did you do yellow first? Okay, so I'll put 6 and then 5 in mine. All right, so you're going to go to stat plot, second y equals. In the first list, you want your yellow ones, whatever list that is in. List 1, list 2 for you probably. And we're picking the box and whisker plot again for the type. Okay, but then go second y equals again and go down to plot 2 and turn plot 2 on. Make sure you hit enter so that it's on. Go over to box and whisker and put the other list in, which for you is probably list 2. And then we're going to try zoom stat and we should see this. Yes, no. Okay, so what's the difference? The first ones we put in, the yellow ones, were near the water. So what can you say? Proximity to the ocean seems to make the wind speed a little bit what? Well, I don't know, the blue ones. Yeah, I would say like the median is just a little bit lower than these. Okay. The 50% that's down here is more spread out. I don't know, there's not a lot of great conclusions to draw here. The median to this one is a little bit higher. The 50% in the middle are definitely higher than the 50% in the box here. So I would have guessed the wind speed near the ocean was going to be more, but that's not what our data showed us for most places. Okay, moving on. Just so you can see that there is a benefit sometimes to describing data separately. We got to go through percentiles and then we're going to do a little normal distribution. Everybody awake? In addition to talking about quartiles, where we did Q1, Q2, or median Q3, you can also look at percentiles, okay, to indicate the relative position of an individual within a set of data. Percentiles divided distribution into 100 equal groups and are symbolized here. The highest percentile would be the 99th percentile. A percentile graph uses the same values as a cumulative relative frequency graph, except the proportions are instead expressed as percent. What in the world does that mean? Well, here's an example, okay? So they have this group of students. There's 200 students in this high school, and they figured out their GPAs. And there was 10 students between 2 and 2.5, and so on, up to 6 students who had between 3.75 and 6. But if you want to figure out the percentile, what you do is you say, here's all the boundaries, okay? We had 10 students, then we had another 28 in this group, then 30, 32, 36, 32, 26, and 6. But you need a cumulative frequency. So you're saying 10 students were this low. Below here were 38 because you're adding these two together. Does everybody see what I'm doing? Cumulative here means you're adding it up. Then we added 30 more students, so 38 became 68. Then we added 32 students, so 68 became 100, all the way to the top. Then you figured out what percent this was. There were 200 students, so they took 10 divided by 200, 38 divided by 200, and figured out the percent. So when they got to the top, this was the 100th percentile. And then I was a little confused what they graphed, but they graphed this right-hand boundary by the percent. So they said 2.25 is about 5%. Here's 2.25, 5%. Like this one is at 350%. 350%. Okay, so here's my question. If you have a 3.7, about what percent are you in this? This would be 3.5, 3.754, right? So a 3.7 would be a little bit below 3.75. So you might be at the 90th percentile. Okay. 50th percentile was people at a 3.0, etc. We're going to do one quick. We have, doesn't tell us what these are, does it even? Okay. Well, whatever they are. Between 55 and 60, we had 3 people, so the cumulative frequency is just 3. Between 60 and 65.5, we had 8 people, or a total of, we're up to 11 now. We're adding these together. Okay, we're going to add 12 more here to 11. We'll be up to 23. Add 5, we'll be up to 38. 28, just kidding. Can't add very well. Add 9 more and we're up to, okay. So to figure out the cumulative percentile, you just divide each one by 37. Okay, I need some typers. Nice loud voices here. 3 divided by 37. Roughly. So about 8%. Okay. Move it over twice or multiply by 100. Everybody good? Now we're going to use the 11 out of 37 because we're including the 3, but we're up to what cumulative percentile now? Okay. Now use 23 out of 37. And then 28. Thank you. And 37 would be 100, right? All right, so what we're supposed to graph quickly is this number and this number. So at about 60, we're going to be up at 8%. At 65, which would be in the middle here, we're up at about 30%. At 70, which is this line, we're up to 62%. I did that right, didn't I? Didn't it? Was it the last number? Okay, suddenly I was doubting myself. Then score of 75 is up to 76th percentile. And a score of 80.5 is about the 100th. So it's very steep. Did anybody else get theirs looking like mine here? So the scores are pretty closely bunched. We could just do that if we wanted at the end, but it doesn't really matter. It says, the question they gave said, estimate the percentile rank of somebody who got a 62. So you can only say, Mom, I got a 62, but at least that's at what percent? So the score of a 62 would be somewhere in here maybe. See what I'm talking about? 62. So what do you want to call that? I don't know, 15%? Does that seem reasonable on your graph or not? It's not a great score either way, but we could say you were at the 15th percentile. It's somewhere in here. It's below 30, but above 8. All right. To be above 50%, what score did they need? So 50% is here. So what score did they need? Yeah, like a 60, I don't know, 68 maybe. It's an estimate. All right, I think we're done talking about those. You now have some work on 11B. You can answer, there's just a couple questions on 11B. All right, but then we're going to move on and start talking about normal distributions for the last 10 or 12 minutes here. I'm just going to sign a couple more problems off this stuff. A normal distribution, okay, is widely used continuous probability distribution that where the graph is kind of symmetric, the mean, median, and mode are towards the middle, the mean, median, and mode are I just said that. The curve is continuous. It approaches but never touches the x-axis, and the total area under the curve is 100%. So this is just talking about when you have data that's fairly evenly distributed. Okay, so not all data looks like this, but if we were to take the heights of everybody in the school, would there be a lot of people lumped between, say, 5'2" and 5'9" or something? Okay, or 5'2" and 6 foot or whatever. There'd be a lot of people lumped in the middle, right? So what this is doing is saying, like, here's they took 100 people and had them run the 400-meter dash, and they got this. Then they said, well, what if we took 1,000 people and had them run the 400 meters? Okay, it's not a dash. I don't know what I just said. It looked like this. Then at 10,000 people, 10,000 times. The more people in the population, the more evenly spread out it was, so that data would be considered to be normally distributed. This is the equation. Would you like to type that into your calculator to have it graph the normal distribution? I don't even know how many parentheses you would need. Okay, the calculator will actually do it on different things. But you can see a larger standard deviation results in a flatter curve. So the standard deviations are how far out you're going each way. So when instead of a whole bunch of data in the middle, if it's spread out more like this, okay, this means the standard deviation is bigger. This means the standard deviation was very small. It's all lumped together. Remember when we talked about that yesterday? Smaller standard deviation means the data is closer together. All right, so this is what we're going to talk about. Last thing we're going to do today is talk about this empirical rule, okay? This is a way to estimate using standard deviations, okay? It says the area under the normal distribution curve between two data values represents the percent of data that falls within that interval. The empirical rule says we're going to just roughly estimate that 34% of the data is one standard deviation each way from the middle. So a total of 68% falls within one standard deviation, either way. Okay, that's the number that they want you to memorize. I'm going to give you a reference sheet. Then 95% falls within two standard deviations. So to this of the mean. So 2 this way or 2 this way. Okay, that would give you 95%. If you go out 3 standard deviations, you're all the way up to 99.7. And even in AP Stats, they say you'll hit 100% by 4, or they never talk about more than 4 standard deviations away. But it doesn't really matter because it actually never hits according to the graph. But the rule they use, it's called the empirical rule, is 68, 95, 99.7. Okay, now let's talk about what that means. You will get a reference sheet eventually. For today, I just want you to use the top of that worksheet. So it says the height of 880 students are normally distributed with a mean of 67 and a standard deviation of 2.5. Okay, so this is what you're going to do when you hear that information. Whoa, that's a bad picture. You're going to put 67 here. You're going to go out 2.5 this way. What would that be, guys? 69.5. And another 2.5? 72. And if you were to go this way, so take off 2.5, you'd be down to 65, 64.5. Did I do that right? And another 2.5 off that would be 62. Okay, it says approximately how many students are more than 72 inches? Well, the rule is this is 50%, okay? This is 34%. Does anybody remember what the next one was on the paper? 13.5. So we need what's left. So we have 50%, 34, 13.5, what's left above that? Okay. That's what they want to know. So we're just using this little rule. Then it goes on to say, be careful, how many actual students? So out of the 880 students, Then we have to do 880 times 2.5 and get about 22 students fell above that. All right, yes. 0.025. We had to move it 2 places. Can you check that for me? Isn't that right? Is that 22? 0.025 times 880? Okay. Then it said what percent fall between 59.5 and 69.5? If I went one more standard deviation this way, I'd be down to 59.5. So basically this is half. And how far did it say? Up to here. So what's half and 34? 50 and 34 is about 84%. Okay, 83.85 or about 84% of the students. Because you're saying everybody down this way plus this 34%. All right, here we go. You have this example. I want you to draw a quick sketch. What does it say is the mean? This is a mean. They do use mu on some of these, I guess. This is the mean, okay, of 65. And they're just using a different symbol. That symbol is called mu. And the standard deviation is 5. So here would be 70, 75, 80. Going this way, we'd have 60, 55, and 50. Okay, so what is this means probability? What is the probability we land between 50 and 70? In other words, what percentage fall between 50 and 70? What's in here? Do you remember? Yes. Okay, now really it's not 100, it's not 50% out here because we stopped here. What was all the way out to 3? 99.7? Is that the rule? 99.7? Okay, cut that in half and we're at what? 48.4? That's probably not right. Someone do that. Somebody do that for me. That's not right. It's 49 point something, I think. What's half of 99.7? Okay, so this was out to 99.7 and we had half of it. So that's why we did divide by 2. Then this additional piece this way was another 34. So what are we hitting? 783.85? Or roughly 84%, which would have been 50 plus 34. All right. The standard deviation of 200 trees in a nursery are normally distributed with a mean of 120 and a standard deviation of 16. So add some 16s and we get 136, add 16 more. What are we up to? Okay, it doesn't look like it goes that high for the question, so I'm going to stop there. 120 minus 16 would be 104. Minus another 16 would be 88. All right, I don't see numbers other than that in the questions, so I'm going to go with this. Approximately how many trees, not a percent, the actual number of trees were more than 136 inches? Okay, how can we figure that out? What is up to here? This is 34% in here, and all of this is forever would be, well, actually, if we said forever, it would be 50, right? So how much is this that is left to be above this? Nope, above the, yes. Okay, so 100% minus 50% minus 34% leaves 16% is above there, okay? But we don't want a percent. How many actual trees were we talking about? Right there it said 200 trees, right? So we need 16% of 200. Shouldn't even need a calculator for that. How many trees is that, guys? 32 trees. Now it says what percent are between 88 and 104. So it wants this little piece. I think that's broken down for you on your sheet. I would have to think about it, but this is 68, this is 97. So I'd have to do 97 minus 50 is 47, cut in half. What does it say on your sheet? Oh, this is 68 in here. So 97 minus 68 is, somebody help me, 29, and then cut in half. But that's not what you have? You got 13.5 on yours? I'm sure theirs is right. What am I doing wrong? Is it not? No, 95. Is the second rule 95 and then 99.7? Yeah. Okay, that's what I'm doing wrong. So this should have been 15 minus 8 is 7. Cut in half is 13.5. All right, so it's 13.5%. It's written on yours, and you get to use that sheet. All right, we're not going to talk about z-values today. So what I want you to do, besides doing, so your homework is to do, what page were those problems on? No. Blah, 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 blah. Yes. It says bookwork from page 660 on 11B. And then I want you on number 14, page 14, 13, 14, 14. I'm just kidding. Page 14. I just want you to do number 2 and number 10. So that you get a little practice with this normal distribution stuff. And then we will do some more normal distribution because that's a huge concept, and talk about z-scores when we're back from break. And then we're going to move on and talk about probability and permutations and combinations and all kinds of stuff.